So last time we discussed about a situation where we consider that the soil is weak, foundation is rigid. So when the soil is weak and the foundation is rigid, we get a reasonably uniform distribution of pressure in the soil, and then if you want, you can actually get the bending moments from a table like this using coefficients. On the other hand, it's possible for us to use a continuous beam, modular continuous beam, and get the bending moments. So that's the method we used. And then we discussed, and we had to rush through in the last part. So today I will not go through it again, because in today's example, I'll be going through most of those things in detail, so that you'll be able to clarify any doubt you have from last week. So today we look at how to deal with flexible analysis. So in the earlier problem, the soil pressure under the footing was considered as constant, but the soil pressure under the footing can actually depend on the deformation of the beam, and if it is fairly rigid and the soil is weak, you will get a uniform distribution. But on the other hand, you can have a distribution where the loads can be concentrated directly under the column if the soil is fairly strong. So in actual condition, pressure varies along the footing, creating high soil pressure under the column. So if you are using a program like sap2000, so we can easily determine the variation of soil pressure depending on the type of loads that are acting on the superstructure. So to do this, first you need to have the superstructure of the building model, and then you have to actually if you want, you can include the substructure or the foundation also into the same model, and then represent the presence of soil as a series of springs. And then when you perform the analysis, it's possible to see the reactions from the soil, to first see whether the reactions will exceed the bearing capacity. And then secondly, you can also see the bending moments and shear forces acting on the foundation, and those values can be used for the structural design purposes. So the main elements involved in the analysis will be the columns, transferring the load onto the footing itself, and the soil. So if you are modeling the substructure and superstructure together, then you don't have to specifically worry about columns. But on the other hand, if you are not modeling the superstructure, then we'll have to we can have the columns and then apply the column loads onto the columns, so that the rest will be looked after by the the finite element modeling part that you do through the software. So to determine the kind of deformation of the soil that can occur, we have to actually look at how to model the soil considering the deformation characteristics of soil. So to determine the deformation characteristics, you can have two types of deformations. One is the short-term deformation, and that is due to the elastic deformation of the soil. But in long run, you know, depending on the type of soil, you can have long-term settlement as well. So if the soil is like sand, then the settlements occur very fast. So basically, we say that as soon as the loads are applied, the settlements will occur. So we don't have to worry too much about the settlements in long term. Whereas depending on the load, there will be an elastic deformation as well. And so what you are modeling here is that particular deformation. So, but if you are expecting long-term settlement due to consolidation, then you may have to make certain allowance in the kind of reinforcement that you provide in the footing to allow for any variations that can occur over a longer period of time. So now to determine the modulus of subgrade reaction, a simple method is given in this famous book on foundations, and the subgrade reaction is defined as the safety factor multiplied by 40 multiplied by allowable bearing capacity. And how you get this 40 is to allow for 25 millimeter settlement. To allow for 25 millimeter settlement, you know, so basically the allowable bearing capacity of the soil represents an elastic deformation of 25 millimeters. So based on that, this particular formula has been developed. And so basically the units of modulus of subgrade reaction is in kilonewtons per meter cubed. And once you multiply modulus of subgrade reaction by the area of the spring that you represent in the model, you can actually see how much the soil is going to deform vertically when you apply 1 kilonewton load. Or you can, on the other hand, you can find the load required to cause a deformation of 1 meter in the soil. So basically the spring constant that you allocate is equal to the load that you need to cause a settlement of a deformation of 1 meter. So you will find the loads that you typically deal with maybe in the range of 5,000, 8,000, 10,000 or even 20,000 kilonewtons to cause a deformation of the soil equivalent to 1 meter vertically. So that is the spring constant that we use. And based on all this information, we can actually, if we are going to model the foundation, then we can actually mount the foundation on a series of springs. And using these springs, you can determine the bending moment that will act on the foundation. And because these springs will allow certain deformation, the bending moment that will occur in the foundation will depend on the stiffness of the foundation. So, and also you can have column loads that vary and spans that can vary. So it gives a reasonable flexibility in obtaining not very accurate results, but some reasonable results. So we often use this particular method to determine the loads that are going to act on the foundation. So what I thought was we'll look at an example, and there may be few in the batch who are not very familiar with FEM modeling. So what I thought was I will very quickly show the creation of the model and also the results. But I have already created the model and the information is all there. So I will not be creating the complete models. Once I create the model to a certain extent, I'll go to the next step with the model that I have already created. So in that way, you know, without spending a lot of time, we'll be able to get the model sorted out. And then we can also see the way that the size of the foundation will be affected by the soil pressure distribution. So you can try a few different values for soil pressure as well, and or the bearing capacity as well. And also we can try different depths for the foundation. So that way we can see how the bending moment distribution and the shear force distribution can vary with few trials. So first we look at the example. A 5-story building has a grid of 4.5 meter, 5.5 meter, 4.5 meters. So you can see it's not a big building, it's a small building. 4.5 meter, 5.5 meter, 4.5 meter. But when it comes to inverted T-type foundations, they can be easily used even when the column grid is about 6 meters spaced, because we will be using a depth of, we can easily go for a depth of about 1 meter, 1.2 meter, and provide a fairly rigid foundation. So because of that reason, you know, even if the spans are something like 6 meters, still it's possible to use inverted T-type foundations. And so here I'm considering not a very big building, it's a small building with spans of 4.5 meter, 5.5 meter and 4.5 meter in one direction. And then in the other direction, that is Y direction, the grid is at 4 meter interval having 5 frames. So, and it's a 5-story building. The column size is 400 by 400. Beams are 500 millimeter depth by 300 millimeter width. The slab thickness is 150 millimeter. And the concrete is 25 megapascal and reinforcement is 500 megapascal. And in this reinforcement, there are 2 types, type A, type B, and type C as well. And type A has less ductility, whereas type B has higher ductility. And what is available in Sri Lanka is type B reinforcement. Type B reinforcement. So what is manufactured and sold in Sri Lanka is type B, which is having higher ductility than type A reinforcement. And generally in Eurocodes, there isn't much restrictions on the use of type B reinforcement. And in certain instances, you will find type A is not encouraged, whereas there's no restriction as such for type B reinforcement. And type C is used in areas having very high seismic activity, because its ductility is even higher. So we are using type B reinforcement. So then the loads are also given. The allowance for finishers is considered as 1 kilonewton per meter squared, and generally we use a minimum value of about 0.75 kilonewtons per meter squared. But here the allowance for finishers is 1 kilonewton per meter squared. uh, which will allow some change in the finishes during the lifespan of the building. An allowance for services is about 0.5 kilonewtons per meter squared. And we'll consider this is an office building. So we are going to have some partitions. And the weight of partitions would be about 1 kilonewton per meter squared. And this is because this is an office building. We'll consider that it will be subjected to a live load of 2.5 kilonewtons per meter squared. And in addition to that, we are going to have a facade, and the facade can be out of windows and some masonry material. So if it is out of 150 thick block work, say hollow block work, so the hollow block work has a density of 12 kilonewtons per meter cubed. And then let's say we are having a plaster of 30 millimeter, having a density of 20. So you can see per meter height, you will get a load equivalent to about 2.4 kilonewtons and per meter height and per meter length. And if you multiply it by the height, let's say 3, we get a value like 7.2. And to allow for any variation like the use of solid block work, if you are using solid block work, the density will be about 20. So then if you are using solid block work, then you will get a value like 3.6 multiplied by 3 will be 10.8, but because there will be openings, we'll make an allowance of 9 kilonewtons per meter, maybe on the little high side, but let's just allow this value for the weight of the facade. And at the roof level, in most of these buildings these days, access can be provided. So because of that reason, generally we consider that the roof slab also will be designed for the same loads, or sometimes even higher loads. If you are going to have special insulation systems mounted, then allowance for finishes and partitions will give a value of 2, and that might be sufficient to allow for any insulation material and additional screed that you might need to provide reasonable thermal comfort. So the soil is expected to have a bearing capacity of 120 kilonewtons per meter squared, and we have to design a suitable inverted T-type foundation. So initially we'll look at the basic system, and then we see what are the variations that we can get as well. So this is the problem. So I will show you very fast how to come to the level like this, where I have applied the loads on the beams corresponding to a unit load acting on the beam, so acting on the slab. So when you look at all these loads, except this particular one, all these loads are acting on the slab. So one possibility is to, if you are using a general purpose software like sap2000, then one of the options available is to consider a unit load acting on the slab, so that we can find the effect of all these other loads, including the self weight of the slab. So on the other hand, if you are using a program like ETABS, then or MIDAS, then the loads can be applied directly. So it's totally up to you. And I will use the method where the unit load will act on the slab, and we see how the loads can be transferred onto the beams. And then we see how these loads can be used to create the combinations as well. So to show you all this, Uh, the models are all there, but I'll just show you how we start with. Can you see the screen with sap2000?
Yes, sir.
You can, right? Oh, good. So what we do is, we'll go with grid only, and we say in X direction we have 4 grid lines, and Y direction 5 grid lines, Z direction 5 grid lines, 5 or 6, 5 floors. Yes, let's keep it as 5 grid lines, and grid spacing in X direction as 4.5 meters. Grid spacing in Y direction as 4 meters, and we say the floor to floor height is 3.6 meters, and we say the grid, all the grids are at 0, 0, 0, and so once you do that, you get a grid like this, and what you can do is you can actually go there and adjust the grid to suit your requirement. And when you're adjusting, rather than using coordinates, it's easier to use spacing. And our spacing is 4.5 meter, 5.5 meter, 4.5 meter. So I can make this 5.5 meter. And then the other direction is 4 meter, so no problem. And I have considered that the floor to floor height is 3.6 meter. So now you can see the adjustment has already happened. So we have the grid with you say okay. So this is the grid of the structure, and then we have to define materials. So there are 2 materials that has already been defined. So this is concrete, this is steel. Because we are going to use concrete, I can just say add a copy of the material, and if you want, you can just give these properties. And but if you want to change the mass of the material later, then better to switch to the advanced properties. So you can go to the properties, material property data. Define materials, add a copy of the material, and if you want, you can switch to the advanced property display. And then it asks what is the material. So we say beam concrete 30 or 25 megapascal concrete. And then you can see the material properties. The elastic modulus of 25 megapascal concrete is about 27. You can get all these details from the Eurocode. And the density is 25. And the mass, you can just leave it as it is. Or if you want, you can make it 2.5. And the strength of concrete is 25,000. And so those are the important properties. And Poisson's ratio can vary between 0.15 to 0.2 for concrete. So we'll use the default value. And once you create one material, you can always copy it to some other material. So you can have column concrete 25, same material, and we can also have a material for slab. Slab concrete 25, but here I'm going to modify this and I'm going to say it's a weightless material. The reason is, you know, for all the loads that are acting on the slab, I'm going to consider unit load acting on the slab and then define the corresponding load. So because of that reason, I do not want the self weight of the slab being counted for the loads. So because of that reason, I'll make it 0. I'll explain it later again. So I will consider that the slab has no weight. And how I do that is by locating a very small value. But when it's come to the mass has to remain, because mass is used to determine the dynamic parameters like the natural period of vibration. So you have to retain mass, but you can say it's a weightless slab, because weight is used for the static load calculations, whereas mass is used for dynamic load calculations. For dynamic load calculations, I'll keep the presence of the slab, whereas for the mass, for the weight, I will consider it as almost 0. So I'm having a slab having no mass, and also we'll need another material, and that is the foundation, FDN concrete 25. But again, you know, you have to see whether it has to be a weightless material or not. The reason is, you know, when you are doing the foundation, there are two methods. One is to take the weight of the foundation into account when you are calculating the total loads on the soil. The other method is, you know, using the net bearing method, net bearing capacity method. So if you are using net bearing capacity, then no need to consider the weight of the foundation when you are doing the foundation design. The reason is when the foundation is long, its self weight is supported by the soil underneath. So the load is resisted where it is applied. So because of that reason, due to the self weight of the foundation, we can't get any bending moments and shear forces. So because of that reason, I can say the foundation concrete is also weightless material. So it has no weight. So I can say okay. And then, so we'll just keep as it is. And then I can define the section properties. So very quickly we'll add few sections, and we'll use concrete and use beam concrete with a depth of 0.5 the depth of the beam is 500 millimeter by 300, 500 by 300. Depth of the beam is 500 by 300. So this 0.5 by 0.3. And so that is beam 500, 300. Okay. And then I'll copy of that column 400, 400. So here you get that. And so that is the column. And I can also define the slabs as area sections, consider it as a shell, and I can say slab 150 and slab concrete, and the thickness is 150. Okay. And then we can save this as all the structures created. So I'll start with BU1. So save as BU1. And I can come to this level. It's not showing anything because we are not drawn anything. And we'll consider height of 3.6 meters. Go to this level, that is the first level. And then, I can actually draw the beam. This way. Can draw it this way as well. I'm using the same beam size in both directions. And then what I can do is get all that, replicate 1, 2, 3, 4 times at 4-meter interval, and delete this one. And in a 5-story building, you will get the concrete walls for some opening for the lifts and so on. But we will not consider any of those things in this simple example. So we can also draw the slab, and you can just draw it. And again replicate. And there you can see that, so here you can't see the slab. So what I can do is, I'll say go to view and ask it to fill the objects. So you can see the slabs is also appearing. And then do is select these points. I could have replicated as well, but it may be faster if I select all the columns and extrude. I'll say extrude the points, frames, column 0, -3, 0.6, and 1. And to allow for the depth of the foundation, I might have Can you see the screen now? I think there was some problem. Can you see the screen now? You can see the sap2000 screen.
Yes.
Yes. Okay. Was there a connection problem earlier for 1 or 2 minutes? So this is the structure, and so once you do this, now we have to see how we are going to apply the loads. And so if you look at the dimensions of these slabs, you can see this way is 4.5 meters, this is 4 meters, this way 5.5 meters, this is 4 meters. So that means, you know, all these slabs are two-way spanning. So in a two-way spanning slab, part of the load will be transferred onto this beam, part of the load will be transferred onto this beam, and this beam will be carrying a trapezoidal load distribution, whereas these two beams will be carrying a triangular load distribution. So we can actually define the loads, and what we do is, you know, we can to define the load patterns like unit slab 1, say it's a live load, and in addition to that we get the facade load, and we'll also get the wind load acting in X and Y directions. So we are getting, these are the basic loads. So if we have a unit load acting on the slab, then we have to see what is the effect, what is the load transferred onto each of these beams. So what I can do is I can select all these beams at the height of 3.6 meters and assign the frame load as unit slab, and the effect is, I'll go to the absolute distance. So this is 4 meters, this is 4.5 meters. So at 0 it's 0, and at 2 meters, this is 4 meters. So the magnitude of the load that will be transferred onto this particular beam will have a value of 2 kilonewtons per meter. So this, so if I draw, I'll show you. So I have a length of 4.5 meter, this 4 meter. So if I get the load distribution, so this will be 2 meters, this will be 2 meters. So here you get 2.0, 2.5, 4.5. So the magnitude of the load will be 2 kilonewtons per meter at this location. So the load will be, here the magnitude will be 2 kilonewtons per So I will so we'll get absolute distance 2 meters, 2, and 2.5 meters, again get 2, and at 4.5 meters, we get 0, and sorry, I should not be selecting this because it has a different load. So I will select only the first span and the last span, and I will say assign frame load distributed, and the values are absolute 2, 2.5, 4.5, and the magnitudes are 2 and 2, and the load case is unit slab, and here I can ask it to display unit slab. So you get that, but you know, in the internal beams you get the load from load from the other side as well. So what you can do is you can just say assign frame loads distributed. Rather than saying replacing the existing load, just say add to the existing load. So you can see instead of 2, now these have become 4, and these will remain as 2. And similarly, you can allocate load for these beams as well, assign frame load distributed, and here you get 3.5 meters and 5.5 meters. The magnitudes are the, and then you select that again, assign frame loads, add, so get that, and similarly you can do the same thing on this side and this side, and this, and you can say frame loads, assign frame loads, and here you get 4 meters, 0, 0, and then again you select these two and ask it to assign frame loads to the existing load. So that way you can get all these loads added fairly fast. So you can see the magnitude of all these internal loads are 4, going up to 4, whereas the external loads are going up to 2. And similarly, we can allocate on the H beams the partition load as well, assign frame load distributed. So here you have to say 0, and here you have to say 9, but the load type is facade, and it's in the global gravity direction. So we can allocate it and ask it to display the facade, and you can see the facade load can be seen. So basically all the loads are there, and so we can save it, and then we can save it as 2, and then so basically so far we have created the first flow of the structure, and we have the basic loads acting on it. And if you display the load assigns, and you can see the effect of unit slab and the facade. So basic loads are there. So it's a matter of now generating it to the number of floors, and then it's a matter of creating the load combinations once we apply a reasonable value for the wind loads. So what we do is we'll take a break now, and after the break at 2 o'clock, at 3 o'clock, we'll 5 minutes past 3, we'll meet again. And if you want to ask any question up to now, you can do so now, or at the beginning, or at any other time. Just ask any question. So do you want to ask any question? Probably most of you are familiar with all this, but I just did this part quickly to make sure that everybody is in the same track. So I'll stop sharing and we'll meet at 5 minutes past 3 and continue from this point.